Hello, hi, thank you for coming. I'm Soham, current data science lead of Big Think AI. And this is Samra as a disembodied voice of the Wizard Boss.
Hello.
And today we're going to be going over a quick lesson. I don't think this is going to take the entire time. But we're essentially going to be combining the topics of the previous lecture, where we're going to show you what it looks like to integrate data science with ML to create essentially what is an entire project and what that entire pipeline will look like, or at least an approximation of it. Share my screen. All right, Samra, can you see the neural net? Can everyone see it?
I can see the beginning of the notebook.
Yeah, that's what we're working on.
Yeah.
Okay. You want to start us off, Samra?
Did you run all of the cells?
Yeah, but I'm gonna rerun them.
Okay. Did you test it?
Yeah, I just wanted to test it. Okay, so let's begin. Hello for anyone who just joined us, and if you just did, today we're just working on neural network with data science. So essentially integrating the two concepts. So let's begin. Samar, do you want to take the top half or the bottom half of the project?
I guess I could do the bottom half as long as we speed run this.
Okay, I can begin. So to start off our project, essentially what we're doing is anyone familiar here with the Titanic data set? So in case you aren't, the Titanic data set is essentially a very classic ML data set of all of the records of every person who was on the Titanic, along with basic information about them, such as their ticket number, fare, where they came from, et cetera, et cetera. The data set will also contain whether or not the person survived the Titanic or whether they unfortunately perished. So it's a very famous data set, and it's essentially very frequently used in ML practices, where our goal is to create some sort of model that can use the existing conditions to predict whether or not someone or a given person will live or die on the Titanic based on the properties given to them. Does that make sense generally? Yeah. Okay. Well, let's begin. We'll start by importing our package. Now we're going to load in our data. Essentially what we're doing here is we're going to read CSV command to load in our data. Here, there are many ways to load in data. Here, personally, you're loading it in from this GitHub link. If you control it should work. Yep. So this is just a CSV that is posted online about all the data of the Titanic data set. And it works. From here, we also call data.head in order for us to get a quick snapshot of the data set. And I'll quickly go over what we have here. So we have a passenger ID that's just like a unique identification number. Nothing crazy going on here. Survive is the main variable that we want to look at. So it's a binary variable that will be either 0 or 1. 0 if the person died from the Titanic incident, and 1 if they survived the Titanic incident. P class, if I remember correctly, should be it should be the level of the ship that they were booked for, with 1 being the lowest level, essentially for people, the lower socioeconomic statuses, and 3 being the highest level for people like the upper class, but the more expensive. Here you have their name, nothing remarkable here. Sex, either male or female, age. Then you have this weird column called SIB-SP. Essentially, it is totaling the number of siblings and or spouses that the given person had with them on the Titanic. So, for example, if we look at Mr. Owen Harris over here, he has a SIB-SP value of 1. That represents, and what that means is that the number of siblings plus the number of spouses that Owen Harris brought onto the ship is equal to 1. Similar issue here with PARCH, which is actually stands for parent-child. It's essentially the number of parents plus the number of children that the person brought on board. For these 5 people, it's all 0. So for all these 5 people, none of their parents and none of their children are brought on board. We also have their ticket number, the fare of the ticket, what cabin they were in, and the port from which they embarked, which had one of 3 options, either C, S, or P, representing different ports that they could come from. Does that general information make sense to everyone? Yeah. Okay. So next we're going to see the folks with their data. So we're going to do data.t types. So these are essentially, this is a command I talked about earlier in the semester. It's essentially a typing command to show the different types of the different variables. As you can see, we have a lot of numeric types, which is good. Numeric is something we're often using on neural nets. But as you can see, we have some stuff that is not numeric. So for example, name and sex are both object variables. Same with the ticket, cabin, and the embarked variables. So essentially, what we have to do is either drop these variables or transform them into numeric variables that can be used in our neural net. So here, we're just going to look at all the unique cabin values. For starters, we're going to get a quick analysis of our data set, just so we can take a look at essentially what we are working with. And the reason this can be very important is that we want to see what we're looking at before we start making transformations to the data. And this will greatly help us to determine how exactly we are going to transform the data set. And here's a great example of this. So originally, when I was going to transform the data set, what I was going to do is it looked like initially, just looking at these, all the cabin values were a letter followed by 2 digits. And so what I was going to do is just separate these two into 2 separate columns, have a letter column and a number column, which seems to make sense until you realize you have this value here, D, which indicates that someone's cabin value is just the letter D. So the previous strategy would not work because they do not have a number. Does that make sense to everyone? Okay. So it's often very helpful to look at these unique values, as that will determine how exactly we are going to transform the data. Sama, quick check. Can everyone in Zoom hear me correct and audibly?
Yep, you're good.
Okay, making sure. This will also just out the number of NaN values, so we can get a closer look at how much data we're going to be dropping later on. And here's how that's calculated. So essentially what we do is we start writing data cabin. So what this does is it just takes the data of the cabin values that was shown above. Then we have this nifty function called dot is NA. What this does is it returns all the entries that are NaN for the cabin values. And from here we just have sum function, and that just sums the number of NA values for the cabin. So we get that there are 687 data points that have NaN cabin value. Now we do something similar for a ticket. As you can see with ticket, it looks like we have a combination of just numbers, and then we have a series of where they have a string and then a number. Since this was very inconsistent from place to place, the way I was going to analyze it was just take the number at the end as the ticket number in order to be consistent, as the majority of entries have a number with the exception of this one. And I will tell you how I dealt with it. And we can see that there are 2 NaN values for embarked, which is a different variable, which we will deal with later. Here we are checking the sex and embarked values, just checking all the unique values to see what we have to deal with, and this will help us in our analysis later on. So here is the first major piece of feature engineering. So I'll take this one through one by one. So first, what we're doing here is eliminating the name variable. Can anyone give a reason as to why we might not want the name when dealing with neural nets?
we can like consider two useful to verify.
I'm sorry, can you repeat that?
We can like convert it to a meaningful numeric, like range.
Yes, that's correct. Thank you. What do you say your name was?
Ishan.
Ishan. Oh, sorry, Ishan. Thank you, Ishan. Yes. So in case you couldn't hear Ishan, what he said was correct was that with the name variable, there is no way to immediately convert that variable column into a numeric variable. And since neural nets can only deal with numeric data, or at least the neural nets that we're dealing with can only deal with numeric data, the variable serves of no purpose to us. So despite the fact that we typically want the name as an identifier, here we are actually going to drop it using the drop command in Pandas. We will specify that the axis is 1 so that the computer knows to drop a column and not a row. In place is just so that we can have this one command and we don't need to set it. Next, we also need to get rid of the passenger ID column from earlier. This was another unique identifier. This one is numeric. However, because it is simply an identifier variable, it's not very helpful to us when we need to analyze things because there's not going to be any correlations to survive. So we just set it as our index, and as a result, we have this. We get to keep our identifier variable without it interfering with the neural net in the future. It's essentially the best of both worlds. Finally, we are going to use the drop NA function, and this will allow us to drop all of the entries that are NaN. What this allows us to do is it gets rid of any data that may have NaN as a value in any spot in any of the columns. The reason we want to do this is because, remember, NaN is not just 0 or, well, it's essentially no. It is not a 0 value. So as a result, if we attempt to train a neural net on a data set that has an NaN value, the neural net will not know what to do. So as a result, we must drop all of the NA. Does that make sense to everyone? And so this is the resulting data set we get. So as you can see, the name column is gone. Passenger ID is now our index, it is no longer a variable, and we will no longer have the NA column, or the NA data. Next, we're going to run this stuff. So what we're doing here is we're taking some of the categorical variables that we're using strings, and we're converting them to numeric variables. So first, we're going to look at the sex variable, and as we saw earlier, sex was either female or male for this data set. So as a result, we have this nifty list comprehension that goes through every string in the sex column. It'll spit out a 0 if the sex is female, and if it's male, it will spit out a 1. So this converts sex into a numeric variable. For embark, we are going to do something a little bit different. So instead of having a longer switch statement or an if then else statement, because there's 3 different possible values, what I did was I made this new dictionary that mapped each of these letters to a certain verb. And what I was able to do here is for each character in embark, I could simply call the dictionary on the character in order to spout out the correct number that they needed, because otherwise it would have been very unusual. This is the result of that. So as you can see, embark and sex are now both on numeric, which is going to be much better for our neural net. Here are 2 functions that I defined to help with feature engineering for the cabin and the ticket, and I will quickly explain what they do. So get ticket num is a function meant for these ticket variable. So as you can see, we have a bunch of these strings, and we want but we have a bunch of these strings, and we want to convert them into a usable variable. So what we're going to do is we're going to use the power of regular expression, which I imported earlier. And we're going to use this function. Don't worry about regular expressions too much. There's always documentation on it. But the TLDR is what this does is it gets the final number from the string for the ticket. And if there was a number in that entry, it'll just return that number as an integer. If not, we will return it. Typically returning 0 in a case where we don't have this case is not the best practice. However, I determined that it was okay for this instance, as here there weren't that many cases where we didn't have them. So is everyone clear on what this function does and its purpose? All right. Okay. So then we have this next function called get cabin info. It's very similar, but it's for the cabin variable, and it's a little bit more complicated. But basically, it's a similar concept where instead of taking just the last number, we're going to take the last letter and the last number. And if they both exist, we will return a tuple of both the last letter and the last number, so they can be put into their separate columns. And if not, we have this quick default case essentially. So that's what that is. Now let me explain what's going on in this. So here we're essentially just implementing the two functions up here in order for our variables to get values. So first we have the ticket variable. And what that does is we are calling our get ticket num function that we described up here on each ticket in the data set in order to transform it into usable data. The cabin is a little bit more complicated, but don't be intimidated. It's actually pretty simple when you break it down. So what we're doing first is defining a dictionary up here that maps each of the possible cabin letters to a number. So we're essentially taking the letter we get and transforming it into a number. Would anyone happen to know why we might want to do this?
The cabin letter correspond to a level of the ship, like a.
Not quite. But they are letters that we are mapping. Well, in case you're stumped, basically it's very simple. The only thing is that with cabin letters, if we kept the cabin letter column as the actual letters, the type of the column would be string or character, which we cannot do for a neural net. Because remember, neural nets can only take in numbers. So as a result, we are forced to convert all the letters into numbers. The idea of them being separate level on the ship, though, was pretty. I'd say that was pretty intuitive. That's what I would have liked as well. But it's just for our neural net purposes. So in any case, what we're doing for the cabin is we are getting the letter and number from the function that transforms the original value into a letter and number. Then we are appending them both to their respective respective lists, while also transforming the letter into its respective number. We then add both of these new lists as separate variables called cabin letter and cabin num. And finally, we drop the original cabin column as we will no longer. Does that make sense to everyone? Okay. We will now run this for statement. This is essentially telling us how correlated each variable is with each other. I know this is a lot of data, but all we really care about is this initial column that, or alternatively the initial row, that relegates everything and shows how each variable is related to survive. Remember, survive is what we're trying to predict. We're trying to predict whether each person on the Titanic is going to live or die. So 1 is the highest correlation, and -1 is the lowest, representing a strict negative correlation. So looking at these numbers, can anyone point out which one is the most strongly correlated? Which of the variables is the most strongly correlated with survive? When not taking the sign into account, just magnitude.
Or could you zoom into that?
Oh, sorry. Is that better?
Yeah, yeah.
Okay.
So did sex most correlated?
That's correct. Despite it being negative, at 0.5, considering that we can go up to 1, sex would be the most correlated. With that, also note that age is the second most correlated when considering just magnitude. At 0.25, and the reason for this is, if you remember on the Titanic, they had a very famous phrase where they first evacuated women and children first, which had to do with sex and age. Hence why these two are going to be some of the strongest correlated. However, note that we do have some other strong correlations, although albeit not as strong, but they still do exist in ticket, fare, and along with even civ SP. So that is something we would want to do.
For sex, 0 was scale 1 in family.
I believe so. We can always check back to our map. Yep. 0 is female and 1 is male. That's why it is negative. Now we are going to do something called normalization for some of the variables. So essentially, when using a neural net, we want to have all of our variables be similar to a normal distribution where they are between 0 and 1. This normalization function is what will help us do it. I know it does look confusing, but it is essentially what it'll do is it'll take each data point, subtract it from the mean for that data point, and then divide it by the standard deviation. So essentially, if the data point is x, we get something like x minus x bar over the standard deviation of x. Does anyone know what this formula looks like from a statistics perspective? Basically, specifically for these scores, but yes, it is the Z-score phenomenon. And that is essentially what we're working here and working towards with this. It'll make it easier for our neural net to comprehend. Let's just find that. Here, this is essentially a check to make sure that we don't have any data that is null, because the neural net will crash on NaN data. So we'll find that. As you can see, it is not here. There's nothing here. Nothing shows up. So that means we're good. We have no NaN data and we're safe. And we finally show the data one last time. And now we're going to work on building our neural net. Summer, do you want to take over for you?
Hello, can you hear me?
They can hear you.
All right. Yeah, so now that we're done with all the data processing stuff, we're going to be doing very similar to what we did last week, where we built a neural network, except we've kind of adapted it in this case. So could you scroll a little bit down so that building a neural network is the first thing? Thank you. Yeah, so as usual, we import our necessary libraries. In this case, we're going to be importing a handy function called train test split that will essentially take our data frame and split it into our training and test sets, as you can see right here. And we're setting our X and Y variables. Basically, the X is going to contain all columns except for our label or answer, or in this case, the survived column, because that's the information we're going to be making our predictions based off on. And Y is going to be our answer column, so it's going to contain only the survived column, as you can see there. And then we're just splitting using that function right there into X train X test, Y train Y test. And if you recall, last time we had this notion of num bins. In this case, since we're doing a binary classification, that is, there are only two possible answers for a question, survived or not survived, number of bins will obviously be 2, and that is the case for all types of binary classification. And right there, there is what the X train looks like after you've converted it to a NumPy array. It's just a bunch of numbers as it should be. There's no, letters or any gobbledygook that will confuse and make the neural network angry. So that's good. And then over here, if we scroll down.
Right, so I'm just gonna run it.
Okay. We are going to be importing our technical libraries as usual, and we're going to be defining the function that we defined last time, which will build our model. Now, I do want to say some things on the actual construction of the layers, because to be honest, at first, the deciding how many layers and how many nodes of neurons you want in each layer can seem quite arbitrary. And truth be told, after doing some research for a lot of times, doing this club, the answer has always been that it is a case of experimentation, meaning to determine, I guess, sort of the best, numbers for how many rows I should put, how many layers I should put and how many neurons per layer. You just have to try it out for varying numbers and see what works best. There are a sort of deterministic methods, such as I think grid search is one of them, where it will literally it's this algorithm which will in a smart way determine the best number of neurons and number of layers just by trying a bunch of different options. But here I just put down some layers with some arbitrary number of nodes. And then, for each of those layers, I put the activation function at the end and making sure that I'm closing out the network with that last softmax layer. And that's where we're, seeing that number bins variable pop up again, because we want there to be 2, because there's going to be 2 labels. So, specify that there's 2 of what's there. And then, yeah, that's it for that cell. You can run that. You've already ran it.
Yeah, I can run it again.
Yep, so just in case I didn't make that clear enough, neural network takes in the input, which is our X train, right? And it passes it through the neural network, does all those computations for us, so we don't have to.
Summer? Something cut off there. Summer, you good? It's not muted, so I'm not sure what's quite going on there. But Summer basically explained the basics of neural networks. So now let's actually run the thing. Oh, okay, you see sound. So this is just a print of what our model looks like. So we have some dense layers here. And it's because we define dense layers here. This is actually what this is what our model looks like. And this is the number of parameters for each model. Don't be scared by the big numbers. It's normal, very normal. And so
Sorry about that. My internet flickered out.
Oh, okay. You back?
Yep, I'm back.
Okay. So we just ran this part while you were gone. I showed them the model. We're now here.
Okay, cool. Sounds good. Yeah, so now we're at this cell. Here we're going to be, what are we doing here? Here's where we're going to be actually training our model. So, just teaching our model how to, predict whether a passenger survived or not, using multiple computations in the neural network. While this runs, I guess let's kind of speak on sort of a guide on how, when to know when to use neural networks. Oftentimes neural networks are used for deep learning, and neural networks are very much used for image-based data, just because of how image-based data is structured versus tabular data, which we have right here. And one big problem about neural networks is that we run into this issue that we call a black box issue. And essentially what that means is that it's not very easy to figure out why the machine learning model made certain predictions, because again, the benefit of having all of this abstracted out for us and that we don't have to do any of this from scratch is that it's easy and convenient for us. But the drawback is that we don't know anything going on inside. So this often comes up in a lot of applications in real life, actually. So oftentimes when a company or business is using a machine learning model, sometimes there will be regulations by government stating that the business has an obligation to explain how the machine learning model works, because oftentimes the output of a machine learning model can have real consequences. For example, for a bank, they may use a model to decide whether to give out a loan. Essentially, the business has to be able to explain why the model works, and it's very hard to explain how a neural network makes its decisions. So oftentimes in applications where explainability is a huge factor, we'll often use models such as decision trees and random forests, which are much better for explaining why this machine learning model made a certain decision, because you can actually trace back which factors. For example, maybe we ran this data set through a decision tree. You'd be able to, through some other tools, you'd be able to figure out that, oh, maybe age was an important factor in determining whether they survived or not, right? And so explainability is a huge factor when determining which model to use. In our case, I believe we'll be mostly sticking to non-image data when we're using neural networks, and that's just because images in and of themselves have a lot to explain. So we're probably not gonna deal with that. We'll know for sure soon enough. But yeah, it's taking longer than I imagined it would take to run.
A high processing computer, most you can, in case you can't tell. Almost done though. More than 2 more epochs. And as you can see, epochs is just the number of repetitions, the number of running the neural net to get the train.
I guess one more thing I can talk about is overfitting. So essentially, if you make your neural network model too complicated, like you add too many layers and too many neurons per layer, the thing is that in your training data, you will probably get high accuracy scores just because you're adding a lot more computational power, and your machine learning models that are able to learn because there's more, I guess, capacity to learn. But the thing is, once you go ahead and run your test data set to see how your model does on unseen data, you'll see a drastic decrease in accuracy. And essentially what's happened is that your machine learning model has overfit to the training data, or it's learned too well to the data that it's seen. It's sort of how when you study for an exam and you get a practice exam, if you do nothing but just memorize the questions of the practice exam, you're not really well equipped to take a new exam, which will have different questions, and you'll probably get a lower score. So it's the same case here. So overfitting is a problem in many machine learning models, but also in neural networks. But yeah, that's something to look out for. And I guess you can run the last block there. Okay, so not a great test accuracy, not an amazing model. Again, like this isn't, we haven't really like done optimization for all the parameters and hyperparameters. So it is what it is, but this is mostly a demonstration. But yeah.
Yep, this was just our quick demonstration on how to integrate data science with machine learning in order to build at least a preliminary model. Does anyone have any questions on this, either in person or in Zoom? Just like we're going here. Summer, you got anything to add?
Nope, I'm good.
All right, then it looks like that is it for today. Thank you so much for coming. I know this is probably a little bit of a walk for those of you that came in person. Be sure to come next time though, especially because that is when I believe we will go revealing the final project to start working on it.